good when I get to this. Where do I start? Balance. So just put 2 beside each of them. So what is put 3 right? I mean, yeah, so you just put 3 in front of you. And then 2 in front of you. Yep. See, that's what I do with very close letters. I feel like I'm just assuming everything I do is wrong until I say that. So when you're getting complex, you put C
oh wait, I was doing too.
It's basically the same thing for the
Not yet. I'm trying to get you to. I'm gonna ask you guys to 20 seconds. If you are done, raise your hand. Okay, let's take 30 more seconds. Cam, do you want to pick? Anthony, do you want to say first? And then Greg, do you want to?
No, I'm just going first. First one all day. Huh, I'm already up.
I love these.
Why the color just?
Oh yeah, you're right.
I'm getting it out. We want you to
Wait.
Okay.
I'm a little slow. So you just put one.
balance. At first. There we go.
I see.
Last one. Okay. I'm trying to watch these kids up here. No, you have to do the second one. You're doing that.
Oh yeah, this. That looks like a chip.
Alright, so Cam is demonstrating that you just put the elements, not with their charges, because they're simply elements. Copper plus phosphorus yields, and now he's going to utilize charges in his crisscrossing fashion as he produces. Let's hope he gets it right, guys. Woo, okay, and balance. That's good. Okay, beautiful, beautiful. Thank you, Anthony. Slide down. That's you right. All right. So the first one was what kind of synthesis? First one and second one were what kind of syntheses? Binary, because they were just element plus element makes ionic compound that you crisscross. The one Anthony's doing is not binary. It's which one? The metal oxide makes the metal hydroxide one, right? And then he has already balanced by nature of having the right formulas. Okay, so chromium 2. That's why we have there's no charges remaining because the subscript's reduced from 2 to 1s. The chromium has a 2 here. One note: I had to tell you this was copper 2. Why? Because you don't know copper's charged because it's a transition metal, right? So if I just said copper with nothing there, you guys would not have been able to get this formula because you would have not known what copper's was. So don't be distracted. Don't put copper 2 in the front. Cam was trying to show us how to think. He put the copper 2 and he thought, he's like, I can't put this here, and he erased it. So that's your process. I only said to do those 3 right there. That's why. Question?
Wait, so we can't write that down? Like, even if it, like, that, like...
Because basically, copper does not equal copper 2. This is a solid, and this is an ion, which is an aqueous form. It's like apples and oranges. Can't compare them. Okay? I know. All right, so quick questions, yeah.
Those are all synthesis, right?
These are all syntheses, yep.
Okay.
So let's do 2 of these together, and then we're gonna check our stuff from last night. Let's do one actually. Let's do barium chlorate decomposes on your own. Start with the barium chlorate. Try to reference your polys in your head. I know it's rough, but it's gonna be with us for at least like another year. So
Wait, what?
polyatomics don't go away. Chlorates break down to lead gas. Not chlorine. Chlorine would kill us all. Oxygen. Okay, that's your gas, okay?
Wait, so
Alright,
does it
what's-
really like just never?
It does not make chlorine gas. So tell me what's barium chlorate. Go.
BaClO.
There's chlorate. There's our 2. Where's our 2?
Outside.
On the outside of, so barium's charged crisscrossed over outside of chlorate, and then we already know one product is what? What's the one gas that's made? Oxygen gas. Okay, so I usually always approach the gas first, and then I can kind of figure out what the other thing is if I have a brain fart and I can't remember it. So what's the other thing made? Barium chloride, because I can't leave out the barium and the chlorine, because then I'll be breaking the law and I'd lock you guys out. Law of conservation of matter. Matter has to stay with us. So what's the formula for barium chloride? Is that? Everybody looking at the periodic table? What's barium charge?
Cl2.
Cl2. Good. And what do I need to balance? Oxygen needs a 3. Okie dokie. All right, so I teach synthesis and decomp together because remember there's 2 that are opposites from each other, and the decomps kind of take a moment to kind of really sink in because those gases are sometimes hard to predict. Hallie?
Why is there 2 on the outside of chlorate?
Because barium has a charge of, and chlorate has a charge of 1 minus. Okay, question over here? Yeah.
Why is it O2? Like, where did you get
Because you have to memorize the 7 diatomic molecules. So the 4 gases that are made in decompositions are in binary binary decomposition. It makes just the non-metals a gas. A lot of times it could be like nitrogen or phosphorus, oxygen, fluorine, can be many gases. What do carbonates break down to form? What gas? Carbonates. Carbon dioxide. That was pretty easy. Chlorates break down to oxygen. You want to say chlorine, but don't. So we say oxygen. And then metal hydroxides break down to form water vapor. Metal oxides and water vapor. But if you remember your gases, your 4 gases, you can kind of figure out the other product. Okay, so let's check our homework from last night quickly, and then we're going to talk about the last 3 test reactions. So I'm going to just leave this here for a moment, and then talk to your neighbor before you ask me, just so we can see what we can explain. Okay? Tell me when you're good on the first step. Next on the board.
I don't know yet.
Wait, hold on. Let me pick number 3.
I got a couple.
Me too. The chlorine is number 4 to substation.
Are you about the reacting? Reacting chlorine has the diatomic.
All right, do is
It's diatomic.
Yeah, they actually
Number 3. What about it?
All right, I'm going to scroll down a little bit. Questions on 1 through 5 up here. I had 2 people ask me questions. More? Hallie?
Number 3. I put a 2 in front of Na2O and a 2 in front of the H2 and then a 4 in front of the NaOH.
So good thought. We have 2 to 2 to 4 ratio. On this example, what did I do to just, it's the same ratio, but what am I showing?
You simplify.
The simplified coefficients, 1 to 1 to 2. If you left it at 2 to 2 to 4, it would be fine, but we do try to simplify everything as we go. More questions on 1 through 5, guys? All right, so I'm going to take your quietness as you're ready to go to the second half. Yeah.
Like for this zinc and chlorine reactants is Cl2. Why wouldn't you have them using zinc?
So Zn, zinc by itself, is just simply a metal. But when it forms an ion, like when it comes to make an ionic compound, that's when we say zinc ion always forms a 2+ charge. So here it's an element. Here it's an ion because it's combined with a non-metal in this case. So here is where zinc formed a 2+ charge and chlorine formed a 1- charge, and they crisscross charges to make zinc chloride. But that's what most people they get messed up on. When the zinc is by itself, it's just a pure metal. Don't charge it because it's not an ion. But when it's in a compound, it has formed an ion and it has crisscrossed its charge already. Okay, let's scroll down to the 1 through 5 on the decomp. I'll scroll down a little bit more in a second. So some of these examples might help you on your problem set. Problem set's just reactions. So we're going to do the single replacements and double replacements today. We'll scroll down just a little bit more here. Because I did a balance. Let's talk about that in a second. Hold on. Just balanced it, yeah. Evan?
Why is silver oxide just silver the one charge?
Ooh, I typed these up. This is not good. Hold on. There's a 2. Superscripts and subscripts are the bane of my existence on typing. Silver oxide, sorry about that. And then, so I needed 2, nope. Yeah. 2 and 4. Whoa, thank you, Evan. Oh. Okay, so keep going. What more? The one I just drew in. So that up there is silver oxide. Silver's number 1. When it forms an ion, oxygen's always a -2, and then we crisscross, we get silver oxide. I balanced it out. So the minute you saw 2 silvers, you wanted the 2 here, but then you saw 2 oxygens. The only way you can make 2 oxygens over here is by putting a coefficient in the front. That modified the silvers to be 4 instead of 2, so we have the 4 over here instead. Okay. And then let's make sure I balance the rest of these. Yeah, I'm good. Okay. Anything else, guys? Talk to me. Like the whole class will benefit. Yeah.
Number 4, aluminum carbonate is heated. I just did that one like totally wrong. I don't know.
Did you just split it in half? What'd you produce?
I got aluminum carbonate yields aluminum 2O3 plus CO2.
You're just in balance. Your products are right. Right? Al2O3, metal oxide, and carbon dioxide. You just have balance.
Oh.
Yeah, coefficients, that's a 3, that's a 1, and that's a 1. Right, another question, guys? All right, so do we feel more comfortable with reactions, like predicting themselves, or do we feel more comfortable with just nomenclature in general? You feel better about nomenclature, right?
Yeah.
Okay, we're going to keep using that nomenclature because that's like your basis. That's going to kind of drive how we draw out and write out these reactions. We're going to keep practicing today and then tomorrow a little bit. Wear shoes just in case we have time for our lab tomorrow. We should, okay? I knew you were going to wear shoes anyway. I'm going to hold off on this example. Okay, so let's add to our foldable. Single replacement, double replacement, and combustion. If you need a marker or a crayon or some sort of other colorful device, they're right here. Otherwise, we're going to be doing some examples, so make sure that you have some extra paper out so that you can have some quality examples. So please write down what's on the board, in your notes or on a flap of your folder. pass back some reference tables just to show you some stuff that eventually will be used. So on the top, you kind of have your definition, per se. That's your single replacement definition. It's literally a single atom or ion replacing a single atom or ion. So as you can see, there is a rule. There's a method to the madness. We don't just willy-nilly replace whatever we want. Cations replace things that can form cations, and anions can replace things that can form anions, or vice versa, but it's cat to cat and to and. So we'll kind of specifically address that in our reaction example. And on your foldable or on your notes, put a big star next to the word that you're writing right here, activity series. This is the only time you will use the activity series. It's when you're presented with a single replacement reaction. It's the only time you'll use the activity series. And here are your two general forms. So looking at your general forms, looking at the reactants, what's the theme you see between the two general forms as like how to identify that this is a single replacement style reaction? Look at it and what's going to look, what do you see happening? So take a minute in there and look. Emma, what do you see happening in both examples? I see you doing this. So, like, give me an example. So C was partners with who in this first example? C was partners with who? B. And then C says, all right, don't like you anymore, B. I'm going to partner with A. Okay? Down here, we have a similar story, but who changed places? So B was partnered with C, and then it changed and switched partners to partner with A. But it's not really B's fault. B just kind of gets put in the mix, and B just has to kind of sit there and bond with whomever is present. So really what's happening is who's trading places in the first one. So it's two of them, right? It takes two to tango. So A and, say again? Who's trading places? So there's two that are switching places. A and B, right? A and B have basically switched places, right? Because now A is with C, but B is booted out to the cold. And then who's trading places in this next one? Who? A and C are switching places. Okay, you guys see that?
Yes.
Okay, it should be very obvious that it's a single replacement reaction because you have a single, like A and A, and then there's a couple, and then one of them gets booted out of the relationship and the other one gets booted to the cold. Okay, so it's a single replacement reaction. All right, so what you can do is first First, let's recognize that, remember in an ionic compound, we have two ions, anions and cations and anions. Who always comes first when we write them out? Cats or ants? Cats always come first, so cations come first. So in this example, this is an element, A is an element. It's not an ion right now. B is a positive charge. C is a negative charge, because that's how it works in chemistry. Opposites attract. I know it's the 21st century, but that's how this works in chemistry. So A and C then would have to be wet and wet. Wet ions. Who always comes first? Cations and then anions. Okay, so then B is just an element again, because it's out by itself. So what did A have the ability to form? A negative charge or a positive charge? Say again? Positive, because you can see it's a positive charge here. So A over here has to be either a metal or a non-metal. What do you guys think? It has the ability to form a positive charge, so it has less than 4 valence electrons, so it's a metal, okay? So A is a metal. So this is basically a metal replacing something that can form a cation. So then down here, where are we different? So B is our positive charge, C is our negative charge, A again is just an element. B here again is what? Positive. You with me, Olivia? A is a, and C is a, or an element. Okay. Okay, so in the case of A this go round, A forms a what charge in the end? Negative. So A is a metal or non-metal? Non-metal. So that's the only difference between these, is sometimes you'll have metals replacing metals, sometimes you'll have non-metals replacing non-metals. Okay? So the way it works is we have to have an example or a single, so A, that is more active on the activity series. So let's look at the activity series. Turn the back of the reference table. And do you see where it says activity series of halogens, activity series of metals?
Yeah.
Okay, so there's all these arrows and all kinds of stuff you gotta read, but basically, the stuff at the top of it, let me actually scroll down here. On our activity series, the stuff at the top are very active. The stuff at the bottom, are very inactive. Who's at the top of the activity series for the metals? Lithium. Who's at the bottom for the metals? Say again? Way down, way down. Gold. Gold. Okay, lithium is super, like, stupid reactive. Why is it so reactive?
Because it's right.
Because it's what? 1 valence electrons. It's like, somebody take my electron, please. Please react with me. I will react with anybody, okay? Lithium is very, very, it's called active, but it's technically just really, really reactive. But gold, I mean, we wear gold. We wear white gold. We wear gold, yellow gold. Does it react with your skin? It could, but does it? Generally not. Does it react with the water if you wash your hands? Generally not, right? So things at the bottom of the activity series are very inactive or non-reactive. If you're sitting next to somebody new, control your urges to talk, please. Thank you. So the things at the top are going to say, I am here to react and I will boot you out of a relationship. Okay? So I need 3 volunteers. Come on up. Come on up. I got copper. I got
Heavy gold.
I don't have gold. Sodium. And I need carbonate. Let's go, Olivia. Okay. You guys all stand up here in the middle. Stand up here, scooch that way some. Alright, so there, guys, they're doing this one. Maybe step to the side just a little bit more, Luke. Yeah. They're doing this example here. Okay, you guys have your activity series, right? So copper's by itself. Where's copper? Raise your hand. Copper, scooch up to the side. Scooch over to the right. Copper, cover up your 2+ charge because you're just cover up your 2+ charge. Copper, cover up your 2+ charge.
Covered up.
Thanks. Okay. Okay. So copper is just singular copper, and then what compound do we have here? Everybody, carbonate. Well, the whole compound. Touch each other. Okay. Sodium carbonate. Okay. So we want to know if copper is active enough to boot out sodium. So everybody look on their activity series. Is copper more or less active than sodium? Why do you say less? Because it's lower down, right? So sorry, copper, you're by yourself. You're never going to get with carbonate. Sorry. Okay, so hold on. Stay. All right, so then we're going to change the situation around. So, right, you can keep it. You can uncover. Cover up your charge. Okay. So look at sodium over there. Hey, sodium, you want to bond with somebody? Yeah, I want to. So sodium, is it higher, is it more active or less active than copper? How do you know it's more active? It's higher, so just get over there and boot, or whatever this is, copper out of the way. By copper, and then copper covers up its charge, and they have bonded. Who didn't do anything? Olivia's just like, I'd like to bond with somebody. I don't really care. Just whomever. I'm good. Easy to get along with. Okay, go back to your seats. All right, I'll take this back. You guys go back to your seats. Thank you, volunteers. Thank you. Okay, so in my young years. So you guys know I have a twin sister, right?
Yeah.
So the two boyfriends in high school could exactly tell us apart. Yeah, identical. So that picture was pretty tough.
Yeah.
Did you guys? Yeah, are they the boys?
Yeah.
No, not that kind. I'm not that.
Is your sister?
So, huh?
Is your sister a teacher?
No, she's a doctor. So anyway, she's a doctor. I prefer to give my time back to you guys and prefer to give time back to the situations. Anyway, so we tried to trick her boyfriend into figuring out who was who, and he totally couldn't do it. She ended up having to break up with him over it. It was bad. So if you can't tell who's who, we can't have this.
You have the same personality.
Similar. I'm way cooler than she is, though. Way. But so this is relevant. Okay, stop interrupting me. Okay, so basically we tried to switch, but the reaction didn't work. So I was like, this guy's horrible. He can't even tell us apart. So she booted him to the side, and my husband now, boyfriend now husband, was totally able to figure it out. He's like, you're Sammy, I got this. I gave him for longer. So we had a little extra help there. But same situation. We tried to switch, reaction wouldn't work, no reaction. And then I actually did switch. I kicked out one of his other girlfriends. So Copper, she was booted to the side, and I was 70. And then I married him. I mean, like, it's legit. We're here. So we have this. Okay. All right. Thank you for that. And there's one more thing I have to say here. Huh? What? Yeah, it is.
Now you know.
Normally I'll have all some videos. Hey, what do you guys need?
Influence, things like that. We do.
I apologize. It's been a busy week for you. Sorry.
You're good.
Bye. Peace. Okay. So on this one, do you guys see this above the metals? Yes. This goes in the same order as the periodic table. Everybody look on the halogen group. Who's the top? Fluorine is the top of the activity series. Fluorine is at the bottom of the halogen group, kinda. Iodine's here. Okay. So who's the most active halogen? Fluorine. Who's the least active halogen? Iodine. Okay, cool. All right, so let's go here. This is, I think, on your lecture notes from yesterday, the big sheet. It's the bigger sheet I gave you yesterday. Okay. Have your activity series right in front of you. We're going to use that to predict if these reactions occur or do not occur. All right, everybody tell me calcium symbol.
Yes.
Ca. And I'm going to show you an alternative way to write water. Instead of writing it as H2O, I'm going to write it as HOH like I did yesterday. H, parentheses OH, and this will help you see the light. Okay? So doesn't this kind of look like A plus BC? A plus BC. Like this is the B and this is the C. So if you see the light, you tell me who is going to switch. Calcium and
Outside hydrogen.
the cation on hydrogen, right? So we're just going to switch calcium and hydrogen. We'll switcheroo. So who gets booted out to the cold? Hydrogen gets booted to the cold. This is my sister's boyfriend, him. Okay. And how do I write that? H2 because it's diatomic. And then who did calcium get with? What? Who did calcium? Calcium got with who? I got with who? hydroxide in what way? Crisscross charges, don't forget that. Ca, OH. Alright, I feel like I'm not talking to anybody. You guys with me? Okay. So now balance. Two in front of what? The water, right? So HOH is just water, right? So do you see there's two hydroxides? So you need two hydroxides over here, so put a 2 coefficient, and that has the two hydrogens you needed as well. Okay? So what did we just do? Look on the chart. Do you guys see where it says calcium can replace hydrogen from cold water?
Yes.
That's what we just did. Now, I didn't indicate it was cold or hot water, but this is what we just did. The calcium is in that span of the arrow, right? So it was able to produce hydrogen gas. What if instead I had chromium? You see where chromium is on the activity series? It's about halfway down?
Yes.
So can chromium replace hydrogen from cold water?
No.
Why are you saying no?
Because of the lines.
Okay, it's not in the arrow ranges, and it can only replace water or hydrogen from steam. So if this were cold water, we would say chromium would be a no reaction because it could not occur. Yeah.
Where the substrate
This one, we crisscross charges. Calcium charge.
Oh, no.
Okay. Just assume I'm always doing that. All right. So can zinc replace the hydrogen from an acid? Look on the list first. Can zinc replace the hydrogen from an acid?
Yeah.
Yeah.
No.
Why are you saying no?
Because it's not in the arrow.
Steam.
It
It
is.
is actually. Oops.
It's the
a long
second. It's the second arrow. Yeah.
Just kidding. I was only looking in that section.
Can everybody point to this on their paper to show the person next to them that they know what we're talking about?
Hey, do you know what you're talking about? Right here. It's okay. I got the same thing. I was looking at the wrong. Yeah, like for some reason I was just looking at the yeah, but it's so in between those. Yeah. He got it.
All right, and come back to me. Come back to me. Zinc. What's the formula for hydrochloric acid?
HCl.
HCl. Who is zinc going to switch with? Why are you saying hydrogen?
It has a higher reactivity.
Okay, but what I just want to verify, you know that zinc is a metal and it could potentially form a positive charge. It's not positive yet, but it can form a positive charge. Who has the positive charge here? Hydrogen. So remember, you're switching cations with cations. So yes, switch those. Okay. Zoe, tell me one product. Oh, you guys were chit-chatting. Come on, help me out. So just pay attention with me. Pay attention or something's going to move. Zane, pick up from there.
H2.
H gets booted out to the cold, but it can't be by itself as a diatomic, and
Plus Z and
Zn and chlorine come together, and they must crisscross charges Cl2. Good, because zinc has a 2+ charge, chlorine has a -1. Okay, yeah.
So before you switch H and Cl crisscross?
They had previously been crisscrossed because H has a 1+ charge and chlorine has a -1. Yep. So this has been crisscrossed before I switch. Yep. So the very first thing is you write your symbols, and then your compound crisscross those charges, and then switch, make your two new compounds, and now let's balance. What do I need?
2 in front of HCl.
2 in front of HCl, and that balances H's and Cl's. Next, bromine plus potassium iodide. Write that out first. All right, Austin, how did you write bromine?
Find it out.
How did you write bromine?
Oh, bromine, BR.
No.
Oh dang.
BR2. I saw a lot of you guys just write BR. It's diatomic. It's in the 7. You got to put diatomic. What's potassium iodide?
Okay.
Ki, because it's a 1 plus and 1 minus with crisscross charges. Okay. And then, hold on. Kelsey, who's switching? Okay, so before we go on, the first two were metals, right?
Yeah.
Metals and metals switched with a positive charge and positive charge. What do we have here?
It's not.
The non-metal, so the non-metal has to switch with the non-metal. So Kelsey, pick up from there. Bromine's the non-metal. Who's it going to switch with here? Iodine, right? So we're going to switch those two, and we make what? Everybody. Who's by itself? Iodine. And is that how you write iodine? No. Diatomic. And then who's potassium with? So that's potassium bromide. KBr, 1 + 1 - crisscross, we're good. And then balance? Very good. Okay, so this was an example of a non-metal with a non-metal switch, if you would like to add that to your thoughts there. Okay, so that's single replacement. How do you recognize a single replacement? What do you see in the beginning? A what? A single element and then a compound, and then one of them switches. Okay? All right, quick questions before I move on to double. Yeah?
How come there's not a table top behind the iodine in the first?
So this is an individual bromine, so we have to write as an iodine. I mean as a diatomic, and then this is in a compound. So if it's in a compound, you don't write the diatomic nature because it's not by itself. Okay. All right, let's go to. I'm gonna skip these right here for a minute. Double replacement. Write this in your double replacement section. Write this in your double replacement section of your foldable. Not really that much. Get ready. Get ready. All right, so I think you can figure this one out. What do you do with the reactants? You just swap either the positive or just swap the negative. Don't do both because then you come back to your original form. But yeah, you just kind of do a little switcheroo on one set, and then you make 2 new compounds. That's it. Yeah. Wow. So that's what we did, synthesis and decomp yesterday, because you're like, okay, I'm open to new reactions, and now you're just like, okay, my brain is full, but we're going to do this. All right, so these are all ionic, generally. Okay, so this little asterisk, this is a generalization. They're all ionic. So what are you doing for every single compound when we write the formula? Crisscrossing charges, and you guys are going to keep forgetting it. That's why I do this exaggerated crisscross charges, okay? Now, if these have charges, what's the charge of A? It's written first, so it's a cation. Okay, B is a or an. Come on, guys. It's an anion. It's bonded. X is a cation, and Y is a or an. Okay, so then that's why A, who is a cation, bonded with Y, who's the anion, and X, who is the cations, bonded with B, who's the anion. You can't put cations and cations together. You can't put anions and anions together. It's just how chemistry is. Opposites attract. Okay? Moving on. Let's do some examples. Oh, there is one thing I did not mention here. So you remember we said put a big star on activity series for single replacement. Put a big star on solubility rules for double replacement. Let's find the solubility rules on our reference table. Do you guys see them? Upper right hand corner. Upper right hand corner. Now there's it's just a lot of words right now, but what we're going to do is apply these here, okay? So basically, soluble versus insoluble. Let's make this note on our foldable or in our notes. What do you think, and let me give you some options. Do you think the word soluble or the word insoluble forms a precipitate? So precipitates are what?
Insoluble.
But what are they, like, technically, what state of matter? They're solids in an overall liquid solution, right? We put liquid 1, liquid 2 together, boom, we make a solid. Evan? Guys, we're not children. Okay. So insoluble means that you are precipitate, meaning that you're a solid in an overall aqueous solution. If you are soluble, what does that mean about you?
You can dissolve in liquid.
Right, you dissolve very well. Do we see you anymore, or are you just kind of distributed homogeneously? You're just kind of spirit fingers, right? You are dissolved in aqueous solution. It means that we don't see you as a solid. Insoluble means we see you as a solid. You are a precipitate. You did not dissolve very well. You guys good with those two terms? I mean, if you know what soluble means, and then the prefix "in" means not, so not soluble means not dissolved. Yeah.
So solute and solution, those go together, right? Like
Solute and solvent make a solution. Yes.
solvent, not solution.
I always
We're gonna get there. We're gonna get there. Okay, we're gonna utilize these. Okay. So here's how you read these rules. This is what you. Is this almost what yours looks like?
No.
I might need to actually. I don't have an actual example. Okay. So under your soluble category, notice I have the ion names, but you guys have the ion. I'm sorry, I have the ion formulas. You guys have the ion names. Do you see under your rules it says all nitrates, acetates, ammonium, and group 1 salts? They're under which category? Soluble. So nitrates, acetates, and ammonium. My ammonium salts are over here, but ammonium salts and group 1A salts, these are always soluble, so it means they're always going to be dissolved. Then there's some exceptions on the next bullet. All chlorides, bromides, iodides are soluble, except for who? So that means silver. So these are the chlorine, bromine, and iodine. So all of the chlorides, bromides, and iodides, when they're in their compound form, they're all soluble, unless you have silver chloride, mercury chloride, lead chloride. Silver iodide, mercury iodide, lead iodide. So we're going to talk about these exceptions in the application sense. So, which ones are generally considered insoluble? What types of compounds? We're going here.
Nitrates, acetates, ammonium.
No, which ones are considered insoluble?
Carbonates, phosphates.
Carbonates, phosphates, and, well, it says that's his except.
Hydroxides.
Okay, hydroxides, sulfides, oxides. So all of those are considered insoluble, meaning that they would form something of a precipitate unless it's bonded with what? What were all those exceptions on the insoluble side? Group 1A. So basically, you know that group 1A is the bond back home, and it's not going to be precipitating, period. It's going to be staying aqueous. So let's look at some examples of these. So these are just compounds, and I want you guys to look at the solubility rules and tell me if it's soluble, yay or nay. So let me walk through maybe one or two with you to get the hang of it. So look at the anion on all of these, because I don't know if you noticed, but these are all listed by anion. So the anion I see up here is what? Who is the anion? Nitrate. So then you look for nitrate in your rules. Where does it fall? Soluble or insoluble? Soluble. Are there any exceptions with the nitrates? Look right here. No exceptions, right? So we would say that this one is soluble. Okay? Look at the chlorides. Where do the chlorides fall here?
Chlorides are soluble.
Okay, are there exceptions to the chlorides? Who? Silver, lead, and mercury. Do we have one of those exceptions?
Nope.
So then we would still consider this soluble. It stays in this column because it still follows the rule. Goodness gracious. Okay, what is this called? S. What? Sulfide. Which category is that? So it's in the insoluble category. What are the exceptions with the sulfides? Okay, so when that say again? Well, so all the sulfides are insoluble except for who is soluble. Group 1A sulfides. Is this a group 1A sulfide? Where's magnesium? It's a group 2A. So does it follow the exceptions?
Yes.
No.
Yeah, what's an exception?
Oh, group 2. Sorry, I thought you guys just said 1A. So yes, it does follow the exception. So it's what? It's soluble. Okay. Phosphates. Where do they fall?
Insoluble.
Insoluble category. So what are the exceptions to phosphates?
Group 1 and ammonium.
And ammonium. So group 1 and ammonium. Is this a group A or group 1A or ammonium? No. So this one is insoluble. So then what's another word for that? Precipitate. Okay. We would see that precipitate as like a white solid. All right, you guys are the last two.
So we can predict the first run of reactants.
Yes, that's what your process.
That's awesome. So the next one will be insoluble.
All right, back to me. 3, 2, 1. Hydroxides and go. Insoluble because the nickel doesn't follow an exception. What's this next one?
Soluble.
This is acetate, right? Acetate's in the soluble category. Okay, so this would be a precipitate, the second one. All right, let's actually do a reaction now. So this is basically, we have reactions, and your job is to be able to predict the products as being soluble or insoluble. That's what the solubility rules help us do. So you guys write the first one out, okay? Do your double replacement. Let's see what you can do first. Nomenclature. Back again.
So one bag?
What? Silver's one. Don't make me do it anymore.
Silver's number one.
Oh, that's why that's
So you can remember it. If I do stupid stuff, you guys remember it. Right?
Yes.
That's not how you should do
No.
Where'd you get the where'd you got
Right. So I know we've even done an example. Let me do this one with you. What did you guys put for silver nitrate?
AG.
AG. AG parentheses if you want. Go ahead. I know. 3. Nitrate has a 1. Silver has a 1. Crisscross. Nothing's there. What's sodium chloride?
NaCl.
NaCl. Okay. So if you want to support yourself forever, here's how you should consider thinking about this. Who's the positive here? Ag. Who's the other positive? Sodium. Who's the negative? Nitrate and chloride, right? Who's silver going to have to get with? Who? Chloride, right? It's the opposite subtract. Opposite subtract. So silver, and how do you write silver chloride? Knowing that silver has a 1 charge. Just AgCl, because silver has a 1, chlorine has a 1. And then who does sodium have to get with?
Nitrate.
Nitrate. And I'm specifically saying sodium first because who do I have to write first in the formula?
Sodium.
The positive ion, right? The cation. So if you put Na or NO3Na, it's going to look ugly. If it looks ugly, it's probably wrong. Okay? So Na plus, NO3, 1 minus, crisscross, nothing, right? So then in the end, we're actually already balanced because everything's 1 to 1 to 1. Okay? So now, look at the two products. Look at the two products. Look at the chlorides and the nitrates solubility rules and tell me their solubility.
all nitrates. That's soluble.
So all nitrates are soluble. Look what I'm going to write to indicate that. It means it's dissolved in what? What is water? Which when something's dissolved in water, what do we call that? Shows with the A. Aqueous. Yes. Okay. AgCl is what? Insoluble. How do I write precipitate? PPT, or I could do a downward facing arrow.
Yeah.
Okay. So that's what you do to indicate solubility. You have to write this on the double replacements. Yeah. You have to. Yes.
Explain why we write those again.
So once you balance, once you predict the products, which were these two products, you write your balanced chemical equation and then you check solubility to indicate.
And then I'll understand what you
You check
No.
solubility. What?
And then that part, I don't understand what you put under AgCl and Na.
Oh, so I specifically want you guys to indicate if something is going to form precipitate in a double replacement reaction. So you checked the chlorines and the nitrates, you said aqueous, and then you said precipitate, so you put PPT, the marker, it's not me, it's the marker. You can put PPT to indicate precipitate there, or you can put a downward facing arrow to indicate the precipitate at the bottom of the test tube. That's it. I'm not sure I explained that. Let me do another example. Quick question.
We're getting this reference table on the quizzing test.
I will give you, not the entire reference table, because as you can see the polyatomics are right there. You guys get the solubility rules and you get the activity series.
So
Okay?
you don't need to
I used to make people memorize them. I'm not as hard of a teacher as I used to be. Okay? Lead two nitrate, and magnesium fluoride. Go. Formula. Lead two nitrate. PB NO3 2. That's lead two nitrate plus Mg F2. We're crisscrossing charges to get those. Okay? This is background. We got this. So go ahead and predict your products and then predict the solubility of those products.
I did the same thing. I need to write. Wait, I didn't actually write the thing below. Like solubility. Wait, no. I'm just confused about the dots. I got PBF2. Oh, okay, then you don't have to do it. Well, I was thinking that was in the other. What was in the last one?
Everybody, after you write your little pluses and negatives, who does lead get with? Lead forms lead. Lead what? Lead what? Lead what? 2 fluoride. Just keeping us on our toes here. It's not. No, so PB is a 2+, fluorine is a 1-, but it's crisscrossing over, but we still call this lead 2 fluoride. Formula is PbF2, but the name is lead 2 fluoride. And then who does magnesium get with? Nitrate, like this? No, so I need parentheses and a 2, and then I need a balance by, nope, I'm good, right? Balanced. All right. What is the solubility of lead 2 fluoride? Insoluble, so it does not match. So fluorides are hard to begin with, but lead is a suspicious character. Usually it's going to be a precipitate, downward facing arrow. What's nitrate's rule?
Soluble.
Always soluble, so how do you tell me? Aqueous. Like aqueous aqua. Okay? So single replacement and double replacement. Give me a thumbs up for both, sideways, down. It's okay if you're on the 50 and up here. Okay. All right, we're going to practice some more, but I'm going to get back to this example, okay? Let's do combustion. I can kill you with practice, but I need to get you some content first, okay? Combustion. Write this on your combustion tab.
Combustion is such a fun one.
The definition is reaction.
So Zane, what's the common thing in both general reactions you see here? Oxygen, right? Combustion literally is any reaction where O2 is a reactant. O2, so reacts with diatomic oxygen. So if you have O2 as a reactant, you immediately identify it as combustion. Now, there's one caveat to that. If you were to just look at this first example, a metal plus a non-metal makes a metal oxide, what does that also kind of look like? Which are the five examples? Or looks like synthesis. Looks like a binary synthesis, right? Metal, non-metal, metal, non-metal, right? It looks like binary synthesis. So if you ever identify this as synthesis, I'd still give you credit because it technically is. It's just we try to identify anything with oxygen as a reactant as just combustion. Question?
But does that share the same formula as synthesis, right?
Yep, that's what I just explained. That binary synthesis is similar to this, how this is phrased, or how this looks. Yep. And then the last example of combustion is actually combustion of things that we like to combust, like things that make fire and flame. Who's ever used like a lighter? You guys know what lighters? Do you never use a lighter? No. So if you've ever used a lighter, what's in the lighter? Butane. Butane is a hydrocarbon. Now I know it's called hydrocarbon, but what's always listed first here? The carbon, right? Back with me, ladies. Hannah and Olivia. Thank you. So I know it's listed as hydrocarbon, but it's not hydrogen and then carbon. It's carbon and then hydrogen. I put X and Y there because we'll put different numbers there to represent different types of hydrocarbons. So the hydrocarbons always produce the same exact thing every single time. Carbon dioxide and water. Where have we maybe seen this before, like in biology?
Photosynthesis.
Photosynthesis consumes carbon dioxide. What's the opposite of that one? Photorespiration. Yeah. Evan.
So rusting is just really, really small combustion, right?
Yes. Rusting is technically combustion because it's reacting with the oxygen. Okay? Alright, so we're going to do some examples with these. You guys ready?
Yes.
Okay? Alright, so, I got to go over nomenclature for organic in a second. I'll do this in a second. I do have to do some. Okay. Let's do this one, and then we'll do this one in a second. Aluminum. What's aluminum? Al. And it doesn't tell you who it reacts with, but the word combust means to react with who? Oxygen. Okay, so this word combust, I will not write, hey, this reacts with oxygen. I'm going to put the word combust. So you must think add oxygen. So add oxygen, and what does it make? So I heard somebody maybe mention CO2 in water. That's only for hydrocarbons, and we don't have carbon and hydrogen here, so you cannot make carbon dioxide. Say again? I hear ALO. It's close.
AL2,
Where are you guys getting these numbers from?
Oh,
Crisscross and charges. Okay, please crisscross your charges. All right, so aluminum, solid, oxygen, gas come together to make aluminum oxide, which is a solid. Balance. What do I need? Keep going. What's the ratio?
Oh, you put a 2 in front of the AL2, and then you put a 3 forward, and then you put a 2 down.
Got you. Okay. Come back to me. Now, I highly doubt anyone off the top of their head knows the formula for octane. It's C's and H's. Okay, you haven't learned this yet, so get ready. Ooh, just maybe by chance, does anybody have their nomenclature lecture sheet I gave them like last week? Nomenclature lecture sheet? No, it's like the lecture sheet that had like ionic, covalent, and acids on it. No, before that. Let's just do a quick search of the notebook.
Oh no.
this one.
Alright, so Emily came prepared. She came prepared. Looks like this.
Yes.
So this in the back. So I have provided you with how to name organic compounds right here, but I also have on the board next. If you have this, then please don't write all this down. You have this for you do have to know how to name organics. Now, guys listen, I did not do this back when we did the nomenclature because you guys were a little overwhelmed. So I backed off and I held off on this so that you'd have a chance to absorb the content. Okay? So, work with me here. So this is going to look at first intimidating, but let's talk through the details. Okay, so organic generally means contains what element?
Carbon.
Carbon. It just means contains carbon. And if you can't see this, this is dark blue, I'm sorry. This organic nomenclature is always going to combine carbons and hydrogens in a certain ratio. So, if you have one carbon in your structure, listen, stop talking to each other. No one's going to get anything out of this. Okay, if you have one carbon in your structure, in your compound, like for example CH4, you start by saying one carbon, but you don't say the word one carbon, you say the word meth. If you have two carbons in your structure, you start your name with F. If you have three carbons in your structure, you start your name with pro. And these are just the prefixes that we use for that. Meth, F, pro, not but, bute, like butane, or propane, or methane, or ethane. Have you heard of these?
Yes.
Potentially, okay.
Phenol.
All right, pentane, hex, hept, and oct. Now, pent, hex, hept, and oct are the same as what? The other ones, the covalent ones, right? The only ones that are different are meth, eth, prop, and bute. So what we have to identify are the number of carbons, and then we'll use that as our prefix to start our name. Please write down this stuff here. 1, 2, 3, if you do not have your paper in front of you. Oh, and this is number of hydrogens. Number of hydrogens, number of carbons. Read what's on the board, people. Okay, just left it there. So notice the difference between the first box, the second box, and the third box. Grant, what's the biggest difference here? Which one?
You asked me what?
I did. Can you please tell me, in the first box, second box, and third box that I have circled in red or boxed out in red, what's the main difference between how I've changed the name?
Subtracting or adding to from two.
Okay, so do you notice the naming, like the ending to these, this, and this? What do you notice is different? How does this change from here to here to here?
The top one's A and ES.
Okay, so ain is the ending to this one,
E and ES.
een, and ein. Okay, so we're gonna then differentiate like propane from propene from propyne, which is based on the number of hydrogens in the structure. Okay, so or isopropyl is actually an alcohol. Okay, so we're gonna get there in a second. So what happens is, and I'm going to do some examples over here on the board, you have to be able to tell me the name of the compound once I tell you what the formula is. So if I give you C2H6, the 2 for carbon is going to pull a prefix, which prefix means 2 carbons. F. And then the carbon number is N. So N equals the numbers of carbon. So looking at this formula here, how did I get to 6? I did 2 times N plus 2. Because 2 is the number of carbon, so it's 2 times 2 plus 2 is what? 6. Which ending does that apply to? Ain, een, or ein? Ain. So this is F. That's F, ain, guys. F came from the carbon. Ain came from the fact that the hydrogens came from the addition, or 2N plus 2. Okay? So let's do another one. I want you to write the formula for propane. So, you know it's a C and a H, and I want you to write propane. So, what does the prop refer to? 3 carbons, okay? What does the ain tell you about the number of hydrogens? Say again? No. The ain tells you how to get to the hydrogens. So 2N plus 2, what's this N right here? The number of carbons, which is 3. So then how many hydrogens do I have? 8. So the formula is C3H8. 2 times 3. Okay. Let's do another one like that. I'm going to keep going until you get it. I want you guys to write the formula for butane. Butane.
C4 carbons.
Hold on. Write the formula down so I know that you're reading it before you shout it out. Wait a second. Alright, Zoe, tell me how many carbons you have in butane. 4. Austin, tell me how many hydrogens you have in butane.
10.
How did you do that? So 2 times 4 plus 8 is 10. Okay? So this is butane. Alright, I'm going to tell you another compound. I want you guys to tell me the formula for pentene. Pentene. Write down your paper. Raise your hand when you're ready. Alright, get me started, Luke.
With CB5,
So the pent means 5, right? So 5 carbons, and how do you get the hydrogens?
we would do 2 times 5 plus 2.
So the 2N plus 2 is for anes, right here. So notice I'm on ene now. So what's the formula? It's just 2N, you see right there? So it would be just 2N. So 2 times 5 is 10. So C5H10. Okay? Let's do another ene. Let's do octene.
Wait, so if you just have an ene, can you just multiply the C by 2?
Yep. Yeah, I'm just showing you the whole process there. Alright, everybody, octene, C, H16. Okay? So now we're going to draw them. Okay? So I want you guys to draw 3 carbons attached to each other with single bonds. Draw 3 carbons attached to each other with single bonds, just in a line. And I want you to get all of the carbons octet by addition of hydrogens to them, bonded off to the side, like we did in our Lewis dot structures. So I want you to draw 3 carbons in a line, connected by single bonds. And I want you to give all the carbons octet by the addition of extra hydrogens to them.
So, we don't put the dot.
You put lines.
But lines. Hydrogen.
So what am I doing over here?
You're adding hydrogen.
How?
With the lines.
3 lines. Okay, so that's hydrogen, hydrogen, hydrogen. And then what do I have here?
2 hydrogen.
2 more hydrogens. And then here, 3 hydrogens. Okay, so this isn't really new because we know octet exists as 2468. So 2468, 2468, 2468. Carbons are good. What's this formula? C what? 3 H 1 2 3 4 5 6 7 8. Okay, what's the name of this formula? So what's the prefix? Pro. And how do you know it's 8? 3 times 2 plus 2 is propane. So this is propane, this is propane, this is propane. Okay? I want you guys to draw, what do I just have? Oh, draw hexene. 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 Try to draw hexene.
Draw it
Like we did this one. Yep, not formula, draw it.
Yeah, that's how I started.
Alright, raise your hand if you drew this on your paper, or something similar. Okay, so let's look at this. This is how many carbons? 6. So this is C6. How many hydrogens? 14, right? So this is what? Hexane. So how do we modify, and I don't know if you noticed this, but it was on the board earlier.
I did not.
it said 2N, and then what did it say in parentheses? So it's a double bond, right? So in the anes, everything is single bonded. It's all good. So we need one of these to be a double bond. And I don't really care which one it is right now. I'm just going to drop off one of these. Let's just drop off this hydrogen over here. So you don't get an extra hydrogen. Instead, carbon, you must do what? Double bond with this carbon. Now, oops, sorry, I forgot the other. See, if you look, or no, that's good. No, not yet. 2, 4, 6, 8. What's wrong with this one?
You have to remove one of the hydrogen.
One or the other. You can do the top one or the bottom one. It doesn't matter. Okay, so then I've modified our structure by dropping off what? 2 hydrogens. So what's our formula now?
So it's
C6H12.
C6H12, and that's hex E. Okay. Now I want you to make this structure, modify it further, and make it hex-ine. Hex-ine. Y-N-E. Hex-ine had 2n minus 2 for the number of H's. So what do you do with the number of H's?
Take 2 off.
Take 2 off, right? So I'm going to take off the 2 that I didn't take off earlier. From where? Left or right? I gotta do the same. I gotta do them same way. So I actually have to take off the 2 more from the left-hand side for you guys, and I'm gonna, instead of making a double bond, make a triple bond. And this new structure is hex-ine, which formula is what? C6H.
You have to.
Yes, because hex means 6 carbons. Okay. So we're gonna actually combust these now. I just want to teach you this first. Yeah. Hexanol. Hexanol. Yep. All right. So let's combust. Hold on. Let's combust octane. Octane. Go. I got 7 minutes. We're gonna knock out a couple more of these. So I need the formula for octane when you're ready. All right. Finish the reaction. If you don't have to draw a picture, I just need a formula right now. That will give you a chance to see the formula. But sometimes pictures help. Oh yeah, let me tell you as well. Alright, give me a thumbs up if you got the reaction written.
Yeah.
Okay. Who got octane written?
Yeah.
Okay, let's start with octane. So Aaron, pick me up. What's octane? Pick up here. So you did C8. Now why are we doing 18? You're right, but why? Good, because this is an ane ending, so you're doing 2n plus 2 to get the number of hydrogens, and the oct is meant for the carbons. Everybody, combustion means add what? Oxygen. Every single one of them, hydrocarbons, will always produce what 2 products? Carbon dioxide and water. So predicting these products are easy because there's really no changes, but balancing them sometimes takes a little longer. Whenever you balance combustion and you have a hydrocarbon example, do it in this order. CHO. Do it in order of CHO. Because the O's are the last one you want to handle because they're in 3 places and you can easily mess them up if you start to do those first. So let's start with the carbons. Well, how many do I need over here? 8. So what do I put in the front right here? A coefficient of 8. Okay. Check. How many hydrogens do I need over here?
18.
So I've got 18 on the reactants. I need 18 on the products, but I only have 2. So what do I need as a coefficient? 9. Okay. Now, when you're counting oxygens, because we did C and H first, counting oxygens, count each of these first. So how many come from the carbon dioxide? So 8 times 2 is 16, and then 9 times 1 is 9. So what's 16 plus 9? 25. All right. So here's the problem. Whenever you have an odd number of oxygens, what the deal here is you're going to have to put what here to make it equal 25? What coefficient will I have to put here to make it 25? 12 and a half, right? I can't put 12 and a half as a coefficient. So, but that's what I wanted you to say. You're good. So since you cannot put 12 and a half here,
Oh, you have to find the greatest
the greatest or least common multiple, right? So what's the least common multiple between 25 and 2?
50.
50. So I need what coefficient here? 25 here, which means I'm going to have to go back and scramble and get these. So basically what I'm saying is if you get an odd number, you're just going to have to double all the coefficients that you would have written. So before I write 25 there, what I would have written, which I think Evan said, I would have put 12.5. And I just put it there just to hold it. I can't have that. So I'm going to go through and double all of my coefficients to modify that. So double this one, what is this going to be now? So it was a 1, now it's a 2. This is going to be what? 25. This is going to be 16, and this is going to be 18. So note to self, maybe write this on your notes. If you get an odd number of oxygens, put your coefficients like you were going to, and then do what? Double them all, because that's the only way you're going to get rid of that half thing, that decimal. Yes, sir.
You think we'll have like some double odd numbers on the whole?
Yeah. Like that's very common in our combustion ones. Okay, so in all, you have the 5 types of reactions under your belt, but you're going to practice. So what I'd like for you guys to do is look at 2 things from here, okay? You guys see this little half sheet?
Yeah.
Teaching. I will leave these as optional for now because you have a problem set in front of you, right? That problem set I want 90% done. Because the only thing you cannot do on problem set is something called NIE, net ionic equation. And if we don't learn them tomorrow, we'll learn them on. Okay? So go ahead and kind of debrief yourself, kind of breathe, practice lessons that you have problem set 11 for tomorrow. It's same like normal half day. You guys had first period ends at 8:05, second block ends at 9, third ends at 9:55, fourth ends at 11. So it's like 55-minute classes. Or 50-minute classes. So problem set 11 looks like this. Okay, eyes up as you pack up. Eyes up as you pack up. You have balancing. I've already predicted the products. Woo, you're just balancing there. Okay, I'm going to scroll down to number 11. Solubility rules. Oh, if you guys want to take a picture of the solubility rules, if not, you'll find it on your online. Take a picture of your reference table, solubility rules.
Is it on your website now?
It is. It's a North Carolina chemistry exam reference table. It's under documents, probably unit 1, probably. And then 12, look at 12. This is where you are writing your own. 12 will take you longer. So if you want to start on 12 while you're still, full of energy, that's where I would start. Okay? Thank you. Markers up, guys. Markers up.